In the last chapter, we understood the power rule visually. Now we will learn how to use it safely when expressions contain constants, multiples, sums, differences, and polynomials. Most derivative mistakes happen because students memorize rules without knowing what the rules mean. This chapter is about building the rules from the idea of slope and small change. A derivative tells us how fast the output changes when the input changes. On a graph, it is the slope at a point. Every rule in this chapter is a rule about how slopes behave. We will study 4 basic ideas: constants, constant multiples, sums, and differences. Then we will combine them with the power rule to differentiate polynomials. Start with a constant function. If y equals 5, the graph is a horizontal line. As x changes, y does not rise or fall. Because the output does not change, the slope is 0 everywhere. So the derivative of any standalone constant is 0. But be careful. A standalone constant becomes 0. A constant multiplying a function does not disappear. It scales the function, and therefore it scales the slope. If a graph is stretched vertically by a factor of 3, every rise is also 3 times larger. Since slope is rise over run, the slope is also multiplied by 3. This gives the constant multiple rule. The derivative of c times f of x is c times f prime of x. The constant stays because it scales the slope. For example, the derivative of 3x squared is 3 times the derivative of x squared. Since the derivative of x squared is 2x, the answer is 6x. Now suppose one function changes by a small amount, and another function also changes by a small amount. If we add the functions, the total change is the sum of their changes. So the derivative of f of x plus g of x is f prime of x plus g prime of x. We can differentiate term by term because small changes add. The same logic works for subtraction. If one function is subtracted, its small change is also subtracted. So the derivative of f minus g is f prime minus g prime. A polynomial is built from powers of x, constants, multiples, sums, and differences. So now all the basic rules begin to work together. Take f of x equals 3x squared plus 5x minus 7. We will not jump to the answer. We will separate the expression into 3 pieces. The derivative of 3x squared is 6x. The derivative of 5x is 5. The derivative of negative 7 is 0. Now combine the pieces. The derivative of 3x squared plus 5x minus 7 is 6x plus 5. Let us try one more. If f of x equals 4x cubed minus 2x squared plus x minus 9, we apply the same rules term by term. 4x cubed becomes 12x squared. Negative 2x squared becomes negative 4x. X becomes 1. Negative 9 becomes 0. So the derivative is 12x squared minus 4x plus 1. Now summarize the rule map. Constants become 0. Constants multiplying functions stay and scale the derivative. Sums split, differences split. Powers use the power rule. Avoid 3 common mistakes. Do not delete constants that multiply functions. Do not forget that x has derivative 1. And do not keep the exponent the same after applying the power rule. There is one thing we are not doing yet. We are not differentiating products like x squared times x plus 1. Multiplication is more subtle and needs its own visual idea. In this chapter, we learn the basic derivative rules needed for polynomials. These rules let us turn many expressions into derivatives without going back to the full limit definition every time. Next, we will explain the product rule visually. We will see why the derivative of a product is not simply the product of the derivatives.